Hi, this is Shivam and today I'll present my project on understanding scene representations for 3D editing. Scene editing is very crucial to the development of augmented and virtual reality applications. Through this project, I want to make decent efforts in better understanding both AR and VR. With the rise in 3D modeling, image editing, and overall progress in graphics, vision, photography, and imaging, we indeed have come closer to better understanding this challenging problem. From NASA teaching astronauts using augmented and virtual reality, to Google translating language in the line of sight, to the famous Pokemon Go game, and to the AI applications of augmented reality for generating enormous amount of synthetic training data, the utility of AR is indeed enormous. But AR is not a new concept. It's been around since 1960s. In fact, if you look closely into this AR invention image, a lot of tools mentioned on it are actually taught in our computational photography course. Despite the early invention, AR is still not a part of our daily lives, and the reason is the challenging nature of the augmented reality pipeline. In this project, we'll mainly focus on the software part of the scene, that is, reconstructing and editing the 3D scenes. In this project, we are given a multi-view capture of the given scene, and we not only want to reconstruct the underlying scene, but also edit it. Towards this goal, we explore two different scene representations, volumetric representation and an object compositional scene graph representation. Let's first dive deep into the volume reconstruction and the editing procedure. We represent the underlying scene as a 3D volume, which allows us to represent the objects in the scene as the sub-volumes. We can then edit the 3D scene by removing and inserting the object as new sub-volumes. We supervise the entire pipeline using the differentiable rendering procedure and also under the diffusion prior or the generative modeling prior of the diffusion models. Let's understand this approach in an experimental fashion. Suppose we are given images of an existing scene. Using the volume rendering literature and the neural scene reconstruction literature, we know we can reconstruct high fidelity radiance fields from the images, just like the one shown here. But what I actually want is to edit these scenes. Suppose I want to remove the flower pot. My training procedure would involve masking out the corresponding regions from the input images and then rerunning the volume reconstruction approach, particularly DVGO approach. Here are some reconstructions from that approach. We can see that the background fidelity is maintained, but the foreground region where the object was removed lacks in fidelity. Not only do I want to improve the fidelity of this region, but also want to insert an object, and that too just using an object. For example, insert a yellow Pikachu sitting on the table. To do so, we leverage the generative modeling prior, or particularly the diffusion modeling prior, using the recently introduced diffusion models. These models have seemed to generate a great amount of naturalist prior of the real world image distribution. Particularly, we use the latent diffusion model, which operates on the latent space rather than the high resolution space. Now, we learn to insert and remove the object by using an inverse graphics procedure where we render a 3D scene volume at different viewpoints, and then each of the viewpoints are passed through the diffusion prior. The diffusion prior updates the scene volume through the naturalness gradient backpropagating via the rendered images. Here are some results from this approach. As you can see, the background fidelity is maintained, the object inserted matches the textual description, we only currently lack in the fidelity of the inserted object. We'll work on this in the future. Now let's dive deep into the second approach of reconstructing scenes as a compositional graph of objects. By representing each object separately, we can easily manipulate and edit them around. Particularly, we can duplicate objects, move them around. We represent each object using a nerve MLP and a latent code. The entire scene can then be rendered by compositing different object nerves and rendering at a particular viewpoint. Here are some results from this implementation. Also note, this implementation was adapted from the original object nerve paper. As we can see, by transforming the crocodile toy, we are able to effectively edit the current scene, but we still lack in little bit fidelity of the underlying scene. We plan to work on this as a future work. Let's now quickly summarize the editable scene representations. In this project, we focused on learning two different representations. One is the volume representation, where objects are implicitly represented as subvolumes, and the other is an explicit representation of the scene, where objects are represented as separate NeRF MLP models. The first volume representation approach allows us to better model complex effects like volume scattering, multi-hit global illumination, etc. While the second approach of scene graph allows us to better disentangle objects from one another and thereby easy editing. Finally, I'd like to thank Professor Yanis for the two amazing courses which inspired me throughout this project. I'd also like to thank Professor Yanis and Professor Deepak for advice during this project. Thank you.